All right, so this is the second video looking at the section on graphing quadratic functions. The focus today is more, as it says, combining transformations together and sketching and visualizing these quadratic graphs in more detail than before, but without just using technology or without just making a table of values. And so first, as it says here, describe how the graph of g can be found by transforming x squared. So the idea is, again, f of x or x squared, that's our simplest possible quadratic function, our basic parabola, and hopefully we can visualize that. It goes through 0, 0, 1, 1, 2, 4. That was part of the last lesson. What we see here for function g is different but related to it. And how is it related? Well, one thing to realize here is the effect of all these parameters. This 2, for example, in the front, that represents a vertical stretch or a vertical expansion. It helps if I can spell. Vertical expansion, most important part's a scale factor by a scale factor of 2. That literally means compared to the graph of x squared, all my outputs, all my y coordinates are going to be 2 times higher, multiplied by 2. As well as, though, there's this minus 3 here. That means 3 to the right. And this minus 1 out here, that's 1 down. Now again, this is all assuming you've seen last video and tried to check your understanding by trying some of the homework problems. Because yeah, what I did there was pretty quick. All right, with that said, though, let's now visualize this graph, again, without just making a table of values. And so, again, sketch a graph of g of x showing at least 3 points. I'll show a lot more than 3 points. And so the first thing I want to do is, all these transformations, these 3 transformations I wrote down, the vertical expansion, 3 to the right and 1 down, make no sense on their own. Like, it's what's been vertically expanded, what's been moved 3 to the right, what's been moved 1 down. Well, x squared. So let's first sketch x squared. And I'll sketch this lightly in gray. So x squared goes through these points. 0, 0, 1, 1, 2, 4, 3, 9, which I can't quite fit on there. So and then it's also symmetrical. So really quickly, without making a table of values, I'm visualizing x squared. There's x squared right there. Okay, so this graph has been vertically stretched by a scale factor of 2 and moved 3 to the right and 1 down. So first, let's visualize the vertical stretch by a scale factor of 2. I'll show that in red. That means all these 5 points I drew, I want to double times by 2 the output, the y variable. So if we look at the vertex, that won't change because the output, the y value is 0. 0 times 0 is 0. All the other points will change, though. For example, if I look at this point right here, the y coordinate is 1. Now, so is the x coordinate, but I don't really care about that. This is a vertical expansion. And so the y coordinate is 1, so now I'm going to double it and make it 2. And looking at this point right here, the y coordinate is 4, the output is 4. I'm going to double it and make it 8. So it's up here. And again, all parabolas are symmetrical, so once I know that, I can just kind of visualize the symmetry here. And really quickly, I have a very good graph of 2x squared. That's what I basically have shown here in red. This is 2x squared. And so now, when I look at that, so if I look up here and see 3 to the right and 1 down, I'm looking at this graph of 2x squared and moving it 3 to the right and 1 down, and then I'm done. So I'll start with my vertex, move my vertex 3 to the right and 1 down. It's right here. There's my vertex. And again, at this point, I'm just translating, so nothing's being stretched or reflected. Same thing for all my points. Take this point here, 3 to the right, 1 down. Take this point here, 3 to the right, 1 down. And again, this graph, I can just copy the same thing for the other points or just make it symmetrical. So here and here. And now, since I'll kind of sketch this nicely, since this is my final answer. And there's my very accurate and quite quickly produced graph of function g, which again was 2 times x minus 3 squared minus 1, I think. Yeah. OK, so the ideas of getting to this visual without, again, having to use technology or without making a table of values, that's fundamental. And that is one of the most important curricular competencies of this course. All right, so similar idea. Let's look at this. What are the transformations for function h compared to x squared? Well, I have a negative in the front, so that's a vertical reflection. I have a +1 here, that is 1 left, and +2 out here, that's 2 up. All right, so again, everything I wrote down only makes sense if I know I'm thinking back to x squared. And so compared to x squared, all this makes sense. And so let's again quickly visualize x squared. 0, 0, 1, 1, 2, 4, symmetrical. Right, notice how fast that was. So the first transformation I want to look at is the vertical reflection. I'm going to reflect this upside down. So I know it actually, if I reflect it upside down, it looks something like this. And reflections are generally pretty easy to visualize. Probably looked in a mirror before. It's not a crazy idea. There we go. So this is minus x squared. That's what I'm showing there. And so that is now what I want to move 1 to the left and 2 up, and then I'm done. So I take all these points and move them, all the points I've shown in red, and move them 1 to the left and 2 up. For example, the vertex will now be up here. My other points will be like this. There we go. That's my graph of h of x. Okay, so notice I'm actually showing 5 points every time for these last few graphs, and it's not taking me very long. I'm not saying it's easy again, but it's not taking me very long. All right, let's move up the alphabet to I of x. So what's this negative 1/2 in the front represent? That represents two things. The negative is a vertical reflection, and the 1/2 is a vertical stretch, or vertical compression is even a better word, by a scale factor of 1/2. So that means all my outputs have been reflected vertically, like before, and compressed towards the x-axis by a scale factor of 1/2, which means all my y-coordinates have been chopped in half and flipped around. And then the +5 here, notice it's not inside the power of 2. It's not inside the quadratic part, so that's 5 up. Okay, so same thing. I'll start with x squared. And hopefully you can visualize x squared as quickly as I'm showing it here. Because again, it is the foundation of this big unit. Okay, there's x squared, 5 points of it. So I want to reflect it and compress it. So I'll do that in 2 steps. So first, the reflection is just like before. Okay, that's my reflection. But before I draw more, my compression is going to be the same as this, but all my y-coordinates are going to be chopped in half, multiplied by a half, divided by 2, all the same thing. A compression by a scale factor of a half, which means I want to look at these 5 points in red, and I want to take their y-coordinates and divide by 2. Well, my vertex still won't change, because the y-coordinate is 0, but all the rest will. I'm multiplying them by a half. And so if I look at this point right here, it's 1 down, or the y-coordinate is -1, it's now going to be -1/2. And same thing with this, because it's symmetrical. If I look at this point right here, the y-coordinate is -4, or it's 4 down. Chop that in half. It's going to be right here, and symmetrical right here. So I'll connect these dots before I forget what the curve looks like. So this right here is my graph of, not quite my answer, but most of it. This is my graph of -1/2 x squared. Both the vertical reflection, so I drew first, and then the compression. I could do that in the other way around. I could have compressed it first and then reflected it. It would have been the exact same. That's the hardest part done. Now I want to take all those points and move them 5 up. So these points here, move them all 5 up, and then I have my final answer. So the vertex will be right here. And if I move all the rest 5 up, it'll look like this. Oh, helps if I can count. All right, and so again, this is my graph of I of x. Now I will say, another thing you could do before I go on is, as we get more proficient with this, once you look at the equation, once you see it's moving 5 up and there's no horizontal translation here, once you know that, you could just immediately draw your vertex right there, because you know the vertex is going to go there. Once you know that there's a vertical reflection, you know it's going to go down. And then instead of going down, by 1 and by 4, as if there was no stretch, you could then chop all those in half. I mean, you kind of look at this in a slightly different order if you want as well. But it all should lead to the same thing. All right, so now, other way around. I'm giving you a function, calling it a of x. You want to tell me the equation. Well, first thing I notice is that it's opening down, but has a vertex right at 0, 3. Which means I know my equation must be of the form, must be a negative in the front. It must be x, just x squared, not plus or minus anything, because I can see the vertex hasn't been translated left to right, but up 3. Which means I don't even need these brackets here. However, what I'm not yet sure is if there's maybe also a stretch right here. Because if I look at this, if I leave it like this, I'm assuming there's a 1 right here, which means there's no stretch at all. Well, I know that can't be right, because what I just wrote down, negative 1x squared plus 3, would look like this. How do I know it would look like that? Because I know the graph of x squared has, if it's flipped upside down, we'll have a point 1 to the right and 1 down, and then 2 to the right and 4 down. Because I know what the graph of x squared looks like if I just flip it upside down. That's not what's happening here. My points aren't 1 to the right and 1 down, or 2 to the right and 4 down. So I now know there's some sort of stretch here. Now again, what I just said is kind of meaningless if we don't already have a good, proficient, confident understanding and memory of what x squared looks like. But what I've drawn in red is just the graph of x squared flipped over and moved up. So now I know there's some sort of stretch. And so I want to visualize it. Let me zoom in here. I can do this visually. For example, I can see instead of being where that red dot is, it's down there. So I can see there's some sort of stretch because it's actually going through this point and I'm showing in blue. Or if I look at these ones down here, I can see, yeah, it's been stretched all the way down to here or here. So compared to the graph I've drawn in red, there's definitely a stretch. So how much farther away from the vertex are these points? These points are all 2 times farther away. Compared to the vertex, compared to where they'd be if there was no stretch, the points in blue are 2 times farther away from the vertex than the graph in red, which means there must be a vertical expansion by a scale factor of 2. Because again, compared to that graph in red, and the graph in red is if there was no stretch, just a reflection, all those points in blue are 2 times farther from the vertex. They've been stretched 2 times farther away. So that's how I know there's not a 1 in the front. I know there's a 2 right here. And the negative because it's upside down. So there's my equation. Now, that I'm guessing the hardest part there was finding that vertical stretch. And fair enough, this is the first example like that. But chances are that's the most abstract part to understand right now at this early stage. Hopefully moving up 3 is fairly clear. Flipping it upside down, I'm hoping is fairly clear as well. So what about this? Same idea. Call this b of x. And so one thing I can see right away is the vertex has been moved to the point 1, 3. So I know and it's been flipped upside down, so my equation must be similar to at least y equals negative bracket x minus 1 squared plus 3. So again, minus 1, so I know the y coordinate's at 1, plus 3, it's moved up 3, the minus because it's opening down. However, again, this might be it. This might be my equation for b of x. However, there also might be a stretch. And so if this is correct, if there is no stretch, it'll go through 1, 3, but the next point will be 1 over and 1 down, 2 over and 4 down, 3 over and 9 down. And it's symmetrical. So what I'm sketching here is the graph of what I wrote, the equation I've written down there, the graph of minus x minus 1 squared plus 3. So again, like before, I know there's some sort of stretch. This time, if I compare these points to what's directly above them, I can see they're being compressed towards the vertex, which means I know this is a compression. Which means I'm multiplying by a number less than 1. but I can't. If I just look at these points here, I can't really tell what I'm like. I could estimate how far down that is, but because that point in blue is not on a grid line, I don't know exactly. It doesn't look like a half. It looks like less than a half. Maybe it's a third. I just don't know of the way down. Same thing with these points right here. I can see it's been compressed from here to here, but I don't know what I'm multiplying by, because again, I don't know where that point is. However, if I look at this point, I do know. If I look from here to here, I can see if there was no stretch, this point here is 9 units down from the vertex. And that's because when you have the graph of x squared, when you go 3 over, you go 9 up. And I've just flipped it upside down. So with that said, this is clearly not going 9 down. This is going, if I look at the graph in blue, whoa, come back. It's 3 down instead of 9 down. And now I can see, because 3 is 1/3 of 9, so all my y coordinates have been compressed by a scale factor of 1/3. Which I kind of guessed from that first one. But now I don't need to guess anymore by comparing how it would look if there was no stretch to the actual graph here. That point right there that I've highlighted in blue, again, is 1/3 of the distance from the vertex vertically, as it would be if there was no stretch. And so that's how I know it's not just negative right here, it's negative 1/3. Now that's it. Again, I feel fairly confident that the trickiest part here is the 1/3 part. And so I will say, if you're unable to figure out that stretch with confidence visually, which is one of the competencies we want to know, well, there is an algebraic take. That is sometimes, at least another option. Okay? And it's something that's essential for this question, because for this question I don't have a graph. So the graph of c of x, I call it. And what do I know about the graph of c of x? I know it has a vertex at 5, -4, and it goes through 2, -1. What's the equation? So for this, I can figure out most of it fairly quickly, as I'll do in a moment, but the vertical stretch of some sort, if there is one, I don't have a nice graph here. Although I could go to grid paper and make a really nice graph, I'm not going to. So I'm just going to visualize something like this. The vertex is at 5, -4. So 5 right, 4 down. Okay, there's my vertex. I know it also goes through 2, -1. So 2 over and 1 down. So about right here. So now I know this graph is opening up, because if 5, -4 is the vertex, I know it has to look like this, and it has to be symmetrical. It has to look something like that. Okay, so now already I know a lot about my graph, or the equation I should say, sorry. I know it's not been reflected, so there's no negative in the front. I know x has been moved, all the points have been moved 5 to the right, so -5, and 4 down. And this might be it. I know there's no negative right here, but I also don't know if it actually is just a 1, because right now I'm basically saying there is no stretch. So I don't know if this number here, I'll just call it A for now, is indeed a 1, a 2, a 1/3. I don't know what it is. And so again, how can I figure it out, especially if I don't have a graph? Well, an algebraic take is to use this point, 2, -1. I know that when x is 2, y is -1. Which means I know, if I change this c of x to y, because again, y is the convention for output, x is the convention for input. I know if I replace x with 2, I know I'm going to get out a -1 here, because I know it goes to that point, 2, -1. So I'm going to put this equation on hold and use that fact. I'm going to replace y with -1, replace x with 2, and notice if I do that, I have only one variable left, and it's the a, which means I can solve for a. I can algebraically find that vertical stretch. And I could have done this for the previous questions as well. And so if I focus on this now, let's clean this up. -1 equals a times 2 minus 5 is -3, all squared minus 4. -3 times itself is +9, so it's 9a minus 4. Add 4 to both sides. So I have +3 equals 9a. Divide both sides by 9. A equals 3/9 or 1/3. And don't forget, the whole point of what I just did was to figure out the stretch. And so now I know there's actually the same sort of stretch as there was in the last question. So let's take that and put it back up there. And so I'll say the equation for this, which I called c of x, I'll say c of x equals 1/3 x minus 5 squared minus 4. And that kind of leads us into our final problem. Which same idea. I'm visualizing the trajectory of something. Now, the trajectory, that means a sort of, if you trace the path of some object in the air, and if you throw something to the air, especially if it's quite aerodynamic, like a ball or something, it'll form a parabola. And if there was no air resistance, it would form a perfect parabola. So the more aerodynamic something is, the more the path of it follows a parabola, an upside down parabola. And that's one of the kind of core foundations of sort of basic physics. And so, like it says, when an object is thrown in the air, the shape of its path, its trajectory, forms the shape of a parabola. Frustrated with your calculator, you kick it like a football and it lands 20 feet away on the ground. If at its highest point the calculator was 10 feet above the ground, find the following: an equation in vertex form that models the trajectory of the calculator. Okay, so, and then the domain and range of the function. So first, I like a visual. So I'm going to draw a little visual here. Okay, here's a person who's angry. Let's see if I can, there's my kicking motion. Let's make this person really angry, because this is important. There we go. Okay, and so there, they kicked the calculator. The path of the trajectory, I said it makes the shape of a parabola. And again, the only reason it's not a perfect parabola, perhaps in real life, is that the air resistance has some effect. But honestly, if you kick a calculator a few feet, air resistance won't have much of an effect. Okay, so there's the calculator has landed right here. And what do we know? We know it landed 20 feet away. So from here to here is 20 feet. And its highest point was 10 feet. Okay, and I want the equation of this curve, this parabola that I've sketched in red. So how can we set this up? Well, I have a lot of ways, but the easiest is to imagine an xy coordinate plane kind of transplanted onto here, where the moment I kick the calculator that's at 0, 0, which means where the calculator lands would be 20, 0, which means the highest point would be 10, 10, halfway over 10 feet up. So now I've actually just sketched out 3 points, including the vertex, of a parabola, which means now it's not much different than the last question. And so, like before, I can say y equals, I don't know what the a is, I don't know what my stretch is, but I know it's negative. I can see it's opening down. But I know that it's been translated 10 units to the right and 10 units up, because the vertex is at 10, 10. And I know, and again, I set it up this way. I could actually set this up differently, but it kind of makes sense to just set up the moment the object was kicked as 0, 0. And all my units are in feet, I guess, in this point. And so, again, I just want to figure out a. How can I figure out a? We'll pick another point, and I can pick either 0, 0 or 20, 0. They're both pretty nice points, but 0, 0 is really nice. So I know when x is 0, y is 0. So I can put this equation on hold and say 0 equals a times 0 minus 10 squared plus 10. That's using that point right there. And I should get this, if I do the same thing with 20, 0, I should get the exact same value for a in the end. So that's it, equals a times 0 minus 10 squared is negative 10 squared. Or let's just save myself some time. Negative 10 squared is 100. So I have 100a right here. Subtract 10 from both sides. I have negative 10 equals 100a, which means a equals negative 10 over 100, which is negative 1/10 or negative 0.1, whatever you like best. Ooh, should have an equal sign there, though. And so now I have my equation for the trajectory of this object. And so I'll say y equals, I'll go with -1/10 x minus 10 squared plus 10. That is the trajectory. That function models the trajectory of me kicking, or I guess it says you in the question. So this is the trajectory of you, of when you kick the calculator. So what's the domain and range of this? So here's the last part. This equation is modeling something. And if I actually did this and measured this, if these numbers were accurate, this is modeling something really, really well. So what's the domain? Well, you may remember that in general, quadratic functions have a domain of all real numbers. But this particular function does not have a domain of all real numbers, because x can't actually be anything. Mathematically, I can put any value of x into here. But in terms of the trajectory of this function, this is modeling, again, the path of this calculator. As soon as x is less than 0, I'm modeling a parabola down here. As soon as x is more than 20, I'm modeling a parabola down here, which doesn't make sense. Once it hits the ground, this equation is no longer accurate. You can't use this equation to model the trajectory of the calculator before I kick the calculator or after it hits the ground. So this equation is only actually helpful, which means the domain of this equation is not all real numbers. It's only numbers from 0 to 20. As long as x is between 0 and 20, this equation will accurately model the trajectory of this calculator. If x is negative, or if x is more than 20, this equation is no longer even close to modeling correctly the trajectory. So the domain of this is not actually all real numbers. The domain is all real numbers, but just between 0 and 20. That's the domain. So again, when a function, in this case a quadratic function, is modeling something, and a lot of things can be modeled really accurately, especially in this sort of Newtonian physics, really accurately with quadratic functions. You have to know when the model is useful. In this case, the model is very useful between 0 and 20 feet for x, but it's meaningless before that. And so the range is not everything less than 10. Again, if we just look at the parabola as a whole, the range would be everything less than 10, because it goes down forever. But again, the trajectory does not go down forever. We're just looking at this region right here. And so the range at its highest is 10, at the lowest is 0. As soon as, again, our outputs, or y values, are negative, this function is no longer modeling accurately. So the range, again, is not everything less than 10. The range is everything from 0 to 10. And when we have questions, applied questions that are using functions to model something, domain and range can get deceivingly tricky. Although in the end, it makes sense. Once I described this calculator getting kicked and hitting the ground, after 20 feet, it's not just sinking into the ground. Even if it was like water, it would still not travel in the path as if it was just an air. So again, this model breaks down. So the domain and the range are hence as you see them written down. All right. Again, fundamental lessons for this course. So take your time with these things.